The Identification and Classification of Minerals by Alan Green. This video is based on a presentation to the High Wycombe U3A's Geology Group, October 2024. Although this video is grandiosely called Identification and Classification, it is in fact more of an introduction to minerals. However, we will cover some of the main identification techniques. So let's begin by defining what a mineral actually is, and what is the difference between a mineral and an ore. A mineral is a naturally occurring inorganic element or compound, having an orderly internal structure and characteristic chemical composition, crystal form and physical properties. Traditionally, a mineral is an inorganic substance, but some people now consider organic compounds to be minerals. However, we'll ignore those people, and we'll stick with the traditional definition. On the other hand, an ore is a naturally occurring solid material from which metal or valuable mineral can be extracted for a profit. So there's no difference really. It just depends on whether or not you can make money out of it. An ore is always a mineral, but a mineral is not always an ore. Mineral classification. Most English-speaking countries, especially the USA, use the Dana classification, developed by American mineralogist James Dwight Dana in 1854. It is based on the chemical composition and structure of minerals, and as mineralogy has progressed, it has been updated many times since. The latest was published in 1997. The original Dana classification was based on 8 specific mineral groups and has stood the test of time. However, there are now 78 classes of minerals in Dana's classification, including many obscure ones. Thankfully, most of those you'll find in the field in the UK fit into one of the original 8. So what are they? Native elements: oxides, sulfides, silicates, halides, carbonates, sulfates, phosphates. Okay, now let's look at each of them in a bit more detail, and I'll include some examples. Native element minerals occur naturally and comprise a single chemical element in pure form, rather than compounds. They are classified into 3 main groups. Metals, examples include gold, Au, silver, Ag, and copper, Cu. Semi-metals, such as arsenic, As, and bismuth, Bi. Non-metals, for instance sulfur, S, and carbon, C, found as diamond, or graphite. Native elements crystallize naturally and are valued for their purity, and in many cases their economic importance. Oxide minerals are a group in which oxygen is combined with one or more metal elements. They form through chemical reactions involving oxygen and metal ions, and are typically characterized by their high hardness and density. Hematite, FeO3, is an iron oxide and exists in a number of forms, as we will see later in this video. Ilmenite, FeTiO3, is a titanium oxide and was once the main source material for titanium dioxide pigments. Corundum, Al2O3, is an oxide of aluminium, commonly used as an abrasive. Khachaturian, SnO2, is a tin oxide and the principal source of tin metal. Sulfide minerals are a group that contain sulfur, combined with one or more metals, such as iron, copper, or zinc. They are often economically important as ores of metals and are commonly found in hydrothermal deposits. Examples include iron pyrite, FeS2, the well-known fool's gold, and galena, PbS, which is an ore of lead. Another is sphalerite, which is an ore of zinc. The name comes from the Greek sphaleros, meaning treacherous, in reference to how easy it is to mistake the darker varieties for galena. The silicate minerals contain silicon and oxygen as their primary building blocks, usually in the form of a silicate tetrahedron. They are the most abundant minerals in the Earth's crust and include various types such as quartz, feldspar and mica. Their structure can vary, forming frameworks, chains, or sheets, which contribute to their diverse properties and appearances. Olivine is a magnesium silicate, often associated with metamorphic rocks. Mica can be either an aluminium or a ferro-magnesium silicate, known for its easily splittable layers of crystals. A feldspar can be any of a group of aluminosilicate minerals containing calcium, sodium or potassium. Feldspars make up more than half of the Earth's crust. Quartz is the second most abundant mineral in the Earth's crust and is a silicon oxide. Tourmaline is a borosilicate present in a wide range of colors and is a well-recognized gemstone. Beryl, also a gemstone, is a beryllium-aluminium silicate. Garnet, often mistaken for ruby, can be found in a range of colors and can incorporate a wide range of metals. Zircon is zirconium silicate and can be found in many igneous rocks. Halides are a group of naturally occurring inorganic compounds that are salts of the halogen acids, e.g. hydrochloric acid. Fluorite is a calcium fluoride, seen here in a more unusual color than the more common purple. Halite, or rock salt, is sodium chloride. Calomel is a mercury chloride. Carbonates are minerals that contain the carbonate ion, CO3₂-. Calcite is a calcium carbonate and in its clear form exhibits the characteristic of double refraction. Siderite is an iron carbonate, and magnesite is a principal source of magnesium. The sulfate minerals are a class of minerals that include the sulfate ion, SO2-4, within their structure. Gypsum is a calcium sulfate used in many building materials. Barytes is a sulfate of barium, commonly known as heavy spar, having a specific gravity of 4.5. Epsomite is a sulfate of calcium, often formed from the evaporation of mineral waters, such as found in Epsom, Surrey, from whence it takes its name. Phosphate minerals are naturally occurring inorganic salts that contain the phosphate anion, PO3-4. They can also include other anions such as chloride, fluoride, and hydroxide, and sometimes arsenate or vanadate. There are over 200 known species of phosphate minerals. Apatite, 5 on Mohs scale, is generally considered to be too soft for use as a gemstone. It is a source of phosphate for fertilizers and pharmaceutical products. Turquoise is a copper or aluminium phosphate, prized as a gemstone. Lazulite is an iron, aluminium or magnesium phosphate, blue in color but not to be confused with lapis lazuli. Mineral identification. The identification techniques to be described are the types which can be carried out in the field or at home. Lab-based techniques, such as crystallography and chemical analysis, although generally definitive, will not be covered here. Several ubiquitous minerals are relatively easy to identify using the field techniques, but given the vast range of minerals present in the Earth's crust, experience is invaluable in making the determination. Practice makes almost perfect. The following characteristics can be useful when identifying a mineral. What is the structure or form of the crystal? What color is it? How lustrous is it? Does it have a characteristic streak color? What cleavage planes are visible, if any? How does it break? How hard is it? What is its specific gravity? Don't worry if you didn't understand some of these. We're going to look at each in more detail now. The study of crystal structures can be a complex subject, but there are a few basic ideas which are of great value in identification of minerals. We will discuss only what these structures are, but not the how or why they are formed. All three-dimensional objects can be described by axes of symmetry, the minimum number of axes to describe a simple shape being 3. Crystal shapes are classified based on a combination of the relative length of the axes and the angles between them. The example shown is 3 axes, all of the same length, all with an angle of 90 degrees between them. The cubic or isometric system has 3 axes of the same length with an angle of 90 degrees between them all. Crystal shapes produced by this symmetry have cubic, octahedral or dodecahedral shapes. Pyrites demonstrates a cubic-shaped crystal structure. Monoclinic. Monoclinic crystals have 3 axes, all at different lengths with only 2 crossing at 90 degrees. The general form is that of prisms, calcite being a well-known example. Triclinic. Triclinic crystals have 3 axes of unequal length, only 2 of which meet at 90 degrees. The crystal forms are prismatic, as in the kyanite example shown, or as a dipyramid. Orthorhombic. Orthorhombic crystals have 3 axes of unequal length, but all meeting at 90 degrees. They again produce crystals which are prismatic or dipyramidal. The example is of an unusually clear crystal of barytes, heavy spar. Tetragonal. Tetragonal crystals have 3 axes all crossing at 90 degrees, with only 2 of the same length yielding prisms, dipyramids, and a combination of the 2. The example shown is a dipyramid of chalcopyrite, a copper sulfide mineral. Hexagonal and trigonal. Hexagonal and trigonal crystals share the same 4 axes, 3 of which are equal length with 3 crossing at 60 degrees and 1 at 90 degrees. The distinction between hexagonal and the subgroup trigonal is based on distinct crystal shapes. Mineral form. Not all mineral samples exhibit pure crystal forms to the naked eye. Most samples encountered will probably have very small and poorly developed crystals, which may be hard to distinguish. These lead to mineral forms which can be very confusing. All of the samples shown here are forms of hematite, an iron oxide. The characteristic form shown on the left gives the mineral its common name, kidney ore. Colour. Although some varieties of a mineral can have distinct and unique colours, for example blue John fluorspar, a mineral may be present in a wide range of colours. To illustrate this, all of these are various forms of quartz. Conversely, a variety of minerals might be described as purple, such as these examples. Therefore, you should not always regard colour as a defining characteristic of a mineral. Lustre. Lustre refers to the surface appearance of a mineral, or what it feels like to the touch. Lustre may be described as metallic, which pretty much speaks for itself, or non-metallic. Amongst the non-metallic group are such descriptors as vitreous, resinous, silky, dull, and greasy. Other descriptions are available. Identifying a mineral as having a metallic luster can greatly reduce the range of minerals to be considered. Streak. The streak of a mineral is the color of the powder produced when the mineral is scraped across an unglazed tile. Streak is sometimes a more consistent color for a given mineral than the color of actual samples, so can be a useful indicator, particularly when impurities are present. Silicate minerals almost invariably produce a colorless streak, so the technique is generally not useful for this group of minerals. Cleavage. This is the tendency of a crystal to split along definite crystallographic structural planes. These planes correspond to the crystal's atomic structure and cause weaknesses within it. When sufficient force is applied to the crystal, such as clobbering it with a hammer, it will split or cleave along these planes of weakness. So, the cleavage planes can tell us about the crystal structure and help to identify the mineral. The following diagrams show some common cleavage types, and you may notice they are reminiscent of the crystal structures we looked at earlier. Mica forms in thin sheets which cleave in one direction only. This is known as planar cleavage. Monoclinic crystals such as feldspar will cleave in 2 directions at 90 degrees to each other. Calcite has a trigonal crystal structure and cleaves in 3 directions, however only one is at 90 degrees. Confusingly, this is called rhombohedral cleavage. Halite, with its cubic crystal structure, cleaves in 3 directions, all at 90 degrees to each other. How to describe cleavage in a mineral? Cleavage quality. How smoothly does the mineral break? Perfect, imperfect, distinct, good, fair, and poor. Cleavage difficulty. How difficult is it to produce a cleave? Easy, hard, and difficult. Crystallographic type. What shape are the cleaved surfaces? Cubic, octahedral, rhombohedral, prismatic, planar, and so on. Many mineral samples will already show cleavage planes without having to resort to examination by bashing it with a hammer. Any flat or slightly irregular surface is likely to be a cleavage plane, particularly if it displays flashes of light as it is turned. Fracture. Not all minerals display cleavage, instead they will break unevenly if struck with a hammer. The fracture characteristic of such minerals is the way they break irregularly owing to weak atomic bonding within the crystal, producing rough or jagged surface. Thus fracture is not related to cleavage, but the way a crystal fractures may aid its identification. Here are some examples of fracture types. Conchoidal, similar to mussel shell ripples. Examples are opal and quartz. Earthy, looks like freshly broken soil. Examples are limonite, kaolinite and aluminite. Hackly, jagged and uneven. This is typical of the native metals, such as copper and silver. Splintery, sharp elongated points and fibrous materials, found in minerals such as chrysotile. Uneven, rough or random irregularities, seen in pyrites and magnetite. Can you spot the odd one out? I'll give you 10 seconds to decide. Time's up. The sample on the left is obsidian showing a very distinct conchoidal fracture, but it's a rock, not a mineral. Hardness. The hardness of a mineral is generally expressed as a value on the Mohs scale. This is a qualitative ordinal scale, from 1 to 10, characterizing scratch resistance of minerals through the ability of a harder material to scratch a softer one. It was introduced in 1812 by the German geologist and mineralogist Friedrich Motz in his book Versuch einer Elementarmethode zur naturhistorischen Bestimmung und Erkennung der Fossilien, or in English, an attempt at an elementary method for the natural historical determination and recognition of fossils. The simple household tools on the right can be used to determine the hardness of a mineral, at least within a certain range. Additionally, anything which will scratch glass has a hardness above 6.5. Diamond is the hardest known mineral, and measures 10 on the Mohs scale. However, Mohs scale is arbitrary and non-linear, that is to say, the steps between relative hardness values are not necessarily equal. Small samples of known minerals on Mohs scale can also come in handy. Refractive index. This is the ratio of the velocity of light in air to its velocity in a crystal. It's not really a field measurement and needs transparent crystals to be able to measure it. However, one particular crystal, calcite, exhibits a phenomenon known as double refraction, making it easy to identify. Specific gravity. The specific gravity of a mineral, also known as its relative density, is a measure of the density of a mineral relative to that of the same volume of water. The density of water is 1 gram per cubic centimetre. The formula for calculating a mineral's density is mass divided by volume. Since 80% of the mass of minerals in the Earth's crust are silicates, with an SG of around 2.7, familiarization with the heft of a few silicate minerals will greatly aid in assessments of other minerals. If a mineral appears to have greater heft than your silicate samples, it is almost certainly a non-silicate. Minerals such as barytes and galena with a notably greater density will be easier to identify in conjunction with the other identification techniques detailed in this video. Fortunately, it's fairly easy to measure the SG of a mineral at home with good accuracy. Measuring specific gravity at home. Thanks to Archimedes and his bath, we can find the volume of a mineral sample at home by measuring the volume of water it displaces when immersed. All you need is a measuring jug marked in milliliters, an electronic Cook scale which can weigh in grams to 2 decimal places, a calculator. Let's find the specific gravity of a piece of sphalerite. Pour sufficient water to immerse the mineral into the measuring jug. Drop the mineral into the water and note the increase in volume. In this example, the mineral volume is 70-50, which equals 20 cubic centimeters. Next, remove the mineral from the water and dry it. Then place it on the scale and read off the weight in grams. Apply your values to the formula. Density equals mass divided by volume. Our piece of sphalerite displaced 20 cubic centimeters of water and weighed 81.61 grams, so its density and specific gravity is 81.61 divided by 20, which equals 4.08. This checks out with Wikipedia, which gives a specific gravity range of 3.9 to 4.2. Now let's put all the bits together. Some common minerals, particularly good samples with good crystal structures, are relatively easy to identify, but become more tricky with poor structures and impurities. This is especially true in the field. You should prepare yourself for field trips by researching the minerals you are likely to encounter at the place you're going to. Ultimately, though, you will find that trial and error will lead you to the correct identification. Like any good detective, use a systematic approach and assemble the various clues into a solution. Don't be afraid to reject some clues and accept others. And as your skills increase, you may find you will revisit previous conclusions and reanalyze them completely. Ultimately, the only surefire way to identify a mineral is by chemical analysis and crystallography where appropriate, but these simple techniques can get you very close. There is always an app for that. Or not. The online apps, rather like plant finders, rely on you taking a photograph of the mineral which the app then analyzes. Unfortunately, as we've seen, appearances can be deceptive, and the app I tried was certainly deceived. As well as wanting me to pay 30 quid a year to remove the adverts, it misidentified 4 out of the 5 common minerals I tried. The one it got right was iron pyrites, which a trained monkey could have identified. So perhaps there isn't an app for that. At least, not yet. Now, let's summarize what we've learned, assuming you've been paying attention. A mineral is a naturally occurring inorganic element or compound with an orderly internal structure, characteristic chemical composition, crystal form, and physical properties. They are generally classified into one of 8 main chemical groups. A mineral's physical characteristics include crystal structure and form, color, luster, streak, cleavage, fracture, hardness, refractive index, and specific gravity. Visual information and physical tests can be used to identify minerals, but experience is also essential because of their wide range and varying physical form. Finally, on behalf of Alan, who wrote the script, me, Sarah, the artificially intelligent voiceover who narrated it, and Phil, who added a few bits and produced the video. Thank you for watching and good luck.